third way of solving scattering problems is with the Born approximation. In order to get to the Born approximation and understand it, we have to start by developing the integral form of the Schrödinger equation. So the first thing is we'll develop that integral equation, then we'll introduce Green's functions, and then we'll talk about integrating the Green's functions to get a solution. So if we start with the time-independent Schrödinger equation, we have E times psi is equal to minus h bar squared over 2m, the Laplacian del squared applied to psi plus v of psi, v times psi rather. And we can rewrite this in a more compact form using k is equal to square root of 2me over h bar, and q, capital Q, is equal to 2m over h bar squared v times psi. So Q contains the wave function times the potential. We can then recast this equation because this is, if we divide by h bar squared over 2m, then we get Q for this term, and we have Q equals del squared plus k squared all applied to psi. If we can find the solution to this equation, which we'll call g of r, for a delta function source, that is over here, instead of a source that looks like q, which is 2m h bar squared v of v times psi, if we replace this with a delta function, and we find a solution psi for this, which we call g of r, so a solution g of r, for the delta function source, then the equation looks like this. Delta, the three-dimensional delta function, or direct delta function, is equal to del squared plus k squared times g of r. Then the solution to the actual source, q, becomes the following. It's just an integral, psi of r is equal to the integral of g of r minus r0 times q of r0 integrated over r0, d cubed of r0. And so basically you're saying this solution of the delta function, if I apply a sum of delta functions, integration of delta functions, I will get the full solution psi of r. Let's see how this satisfies the Schrödinger equation. So let's start by del squared plus k squared applied to psi of r. That's the right side of the equation. Now we put this solution psi of r in for this. So that becomes then an integral of the quantity del squared plus k squared applied to g of r minus r0, q of r0, d cubed of r0. But del squared plus k squared applied to g of r minus r0 is just exactly this equation up here, which means that if I replace g of r minus r0, r with r minus r0, this is just a delta function of r minus r0. So I can replace everything that's in the red here with a delta function, del cubed of r minus r0 times q sub of r0 integrated over d cubed of r0. But that is a trivial integration because when we integrate with the delta function, we just replace r0 by r. And so this gives you, integral is done, you get q of r. And so this brings you back to the actual solution of the Schrödinger equation, which is rewritten as q is equal to del squared plus k squared applied to psi. And in fact, del squared plus k squared applied to psi is equal to q of r with this form of the solution. And g of r being the solution for the delta function driving force, or source for this equation. Now, g of r is called the Green's function, and it represents the response of a linear differential equation to a delta function source. When you determine the Green's function, you can then solve a differential equation's response to an arbitrary source using a simple integral equation. So this is a generalization of what I just explained in the last slide. The task then is to solve the delta function source equation for the Green's function, and then apply the simple integral equation to get the full solution. So the delta function source is equal to del squared plus k squared applied to g of r. We can solve this by taking a Fourier transform. So let's take and assume that g of r is a Fourier transform of another function g of s, lowercase g of s. So g of r is 1 over 2 pi to the 3 halves, because it's a three-dimensional function, times the integral of e to the I s dot r, g of s, d cubed of s, integrated over s. And s is three-dimensional. It has s theta and phi. S theta sub s theta sub phi. Phi sub s, rather. So now, when we apply the right side of this differential equation to g of r, we get the following. So we apply del squared plus k squared to g of r. We get 1 over 2 pi to the 3 halves. And then we can pull these operators into the integral because they depend on k, not on s. So they can go in and out of the integral with impunity. They work on the r space, but not s space. You have then the integral of the quantity del squared plus k squared, this is del sub r, applied to e to the I s dot r g sub s, g of s, d cubed s. Well, this term here is just equal to a delta function, because the delta function is the source. So this now is, the delta function is then equal to everything that's on this side. Now, if we take s del squared and apply it to s dot r, e to the I s dot r, it doesn't apply to g because g depends only on s, but e to the I s dot r depends on r. We can rewrite this and apply that second derivative, and we get 1 over 2 pi to the 3 halves, integral of minus s squared, because when we take that derivative, we pull down s squared, plus k squared, all applied to e to the I s dot r times g of s integrated over s. But the delta function, there's another representation that we can make of the delta function, which is 1 over 2 pi cubed times the integral of e to the I s dot r d cubed of s. So that's a fully equivalent representation of the three-dimensional delta function. And so we now have this integral over here is equivalent to this integral over here. So by inspection, we can then extract what g of s is. Because if these two are equivalent, well, we have a constant, 1 over 2 pi to the 3 halves. Then we have that here we have e to the I s dot r. Here we have e to the I s dot r, but it's multiplied times k squared minus s squared and g of s. So that means that g of s, over here you have 1, over here you have all these other quantities, is equal to 1 over 2 pi to the 3 halves times k squared minus s squared. And so g of r, capital G of r, once we replace g of s here, becomes a rather straightforward integral. It's 1 over 2 pi cubed, integral of e to the I s dot r times 1 over k squared minus s squared integrated over ds cubed. So we have to solve the Green's function by doing this integral. So how are we going to do it? We first choose the spherical coordinates with the polar axis fixed along r. The polar coordinates for s. We're going to choose spherical coordinates for s with the polar axis, the z sub s, along the r vector. Well, that means that s dot r is just s times r times cosine theta, And the phi integral is just 2 pi because there is no dependence on phi anywhere. And we now have an integral that looks like this. 1 over 2 pi squared, because we canceled one factor of 2 pi from the phi integral. Integral from 0 to infinity, integral from 0 to pi of e to the I sr cosine theta over k squared minus s squared times s squared sine theta d theta ds. Well, the theta integral can be done, right? We ignore the k squared and s squared and the ds, and we just take the integral in red here. And that integral is really straightforward because it's the perfect integrand of e to the I s dot sr cosine theta over ISR, evaluated, and now we evaluate from 0 to pi with a minus sign in front. And this just gives you 2 sine of SR over SR. So that integral is very straightforward to do. Then g of r is equal to 1 over 2 pi squared times 2 over r. The r is not part of the integral, can be pulled out. Times the integral of 0 to infinity of s sine of SR over k squared minus s squared ds. If we now combine all these factors out here, and we realize that this is an even, even around the origin, we can make this an integral from minus infinity to infinity dividing by a half. So it's half of the integral from minus infinity to infinity, and that gives us 1 over 4 pi squared r, integral from minus infinity to infinity of s sine of SR divided by k squared minus s squared ds. And this is the final integral that we have to do. But that integral has some problems. And the reason we have some problems is it has a pole. It has where s is equal to k, or s is equal to minus k, this integrand goes to infinity, and we can't integrate it through s. And so we need to do this by using Cauchy's formula. So the integral that we have to do has 2 poles at k and minus k. And we're now going to rewrite this so that we can use Cauchy's formula. So we'll use that e to the ikx minus e to the minus ix rather is equal to 2i sine of x. So we can replace the sine of SR with 2 terms. The first, and so we have 1 over 8 pi squared. We have the 2 that floats in. Then we have the quantity integral from minus infinity to infinity s e to the ISR over k minus s times k s plus k. That's just k squared minus s squared. Integrated over ds minus the integral from minus infinity to infinity of s e to the minus ISR over k minus s, k s plus k integrated over ds. Now I'm going to take this, and if I bring the I above, I have a minus sign, and that allows me to flip the sign inside these. And so I get, instead of k minus s, I get s minus k, and s minus k here, because of the double minus sign. So the integral is the same, except now you have s minus k and s plus k in the denominator. So g of r is then equal to I over 8 pi squared r times integral 1, which is this first one, minus integral 2. Now both integrals are formed where we can apply Cauchy's integral formula. And Cauchy's integral formula says the following. If I have a path integral, a complete path integral, a closed path integral of a function f of z divided by z minus z0, so a function where there's a pole along the z-axis, integrated over dz. And I can go around this pole and integrate around the pole in a clockwise way. The integral around that pole will just be 2 pi times I times the value of the function at the pole. f of z0. And that only holds if z0 lies within the contour. Otherwise, you get a 0. So in this case, we have pole singularities along the path of integration, right? We have s minus k here and s minus k here. And so we have an s plus k, so we have poles that we have to deal with. So we need to avoid the poles and integrate around with contour using Cauchy's formula. And we can do that relatively simply. So here's Cauchy's formula again. And we're going to choose a path that looks like this. We're going to start at minus infinity along the real part of S. There's a real part, we have a real part and imaginary part of S. We're going to start at minus infinity along the real axis. We're going to integrate around here. Then we're going to take a tight loop around the pole at minus k in the positive direction. Then we're going to take a tight loop around the pole in the negative direction and then go again to infinity. So we deform the path to loop around the negative pole in the positive direction by an infinitesimal amount and around the positive pole in the negative direction by an infinitesimal amount. And then we're going to close the contour at real plus or minus, the real part of S goes plus minus infinity in a semicircle so that the absolute value of S is infinite. So that means that way out here, we're going to close going around one direction or around the other direction. So in one case, we go around the pole at positive imaginary S, and the other way we go negative imaginary S. So let's do the first integral. The first integral is I1, is the integral where we're going to do a contour integral of s e to the ISR over s plus k times 1 over minus s minus k ds. We're going to close this in the positive imaginary s direction so that this pole at plus s is included, so that's this term here, and this pole at negative k is excluded. So we then have to evaluate, the Cauchy formula tells us that our solution is 2 pi I times the function at the pole if we go in the counterclockwise direction. So we're going in counterclockwise direction around the loop. And so we need to evaluate s e to the ISR over s plus k at s equals k. But of course, we've excluded that in the pole, and so that's the pole we integrated out, and so there's no infinity anymore. At s equals plus k, you just get 2k. And so this gives us I pi times e to the ikr. You have 2k here, cancels the 2. You get a pi I, and here up here you get k, which cancels the k on the denominator, e to the ikr. So you get I pi times e to the ikr. Now we're going to go in the negative direction, the clockwise direction, around the negative infinity for imaginary s for the second integral. And the second integral has a minus sign in front of it. It's s e to the minus ISR over s minus k, and then we have the pole at 1 over s plus k integrated over ds. And again, here we have minus 2 pi I, s e to the minus ISR, s minus k over s minus k, evaluated at s equals negative k. Now, why do we have a minus sign? Because we're going in the opposite circular direction. And so now, when we put this together at s equals minus k, you get s becomes k, and here we have a negative k, and we get minus I pi e to the ikr. So we have 3 negative signs, and one of them remains. So this minus sign is pulled through. Therefore, we can add together these solutions. g of r is equal to I over 8 pi squared r times the quantity I pi e to the ikr minus a minus I pi e to the ikr. We put this all together, we get minus e to the ikr over 4 pi r.